Welcome to Denver Startup Week. I'm Ben Data, co-chair of DSW. This year marks the 10-year anniversary of Denver Startup Week. This community has been the catalyst for lots of change over the past decade, and this week we're coming together to celebrate the past and dream big for the future. We are able to bring Denver Startup Week to this community thanks to our 2021 sponsors. Thank you to our HQ and title sponsor, Amazon, and our title sponsors, whose leadership makes this week come to life. Capital One Cafe, Downtown Denver Partnership, Fluid Truck, Hotel Engine, and WeWork. And our track sponsors, who have made all of the great content you're hearing today possible. Founder Track, Kickstart, Growth Track, Friday Health Plans, Developer Track, Quizlet, Product Track, Palantir, Designer Track, Battery 621 in the Public Works, People Track, Exactly, and Spotlight event sponsor, Strat Labs. Our headline event sponsors are bringing the excitement this week. Thank you to B-Side Fun, Colorado Public Radio, Comcast, Coors Brewing Company, Denver Pavilions, Entrepreneurship at the University of Denver, Gusto, JP Morgan Chase, Method, Moss Adams, Pine Insurance, Promontory Mortgage Path, Red Bull Basement, Southwest, Tattered Cover, and VF Venture Foundry. Finally, thank you to our partner and member sponsors listed on the screen. Please say thank you to these companies as you enjoy our hybrid Denver Startup Week. And don't forget to use hashtag Den Startup Week to share your experience and moments of inspiration on social media. Have a great week.
Early risers, all-nighters, slow pours, fast crams, post-nap, on the mat, in the stacks, phone down, volume up, complete silence. You ups? Coffee cups, pizza crusts, first semester, fourth quarter. Focus 100, privacy 0. Pre-test, one last check, let's go. However you study, Quizlet takes the guesswork out of your coursework. Learn it, own it, Quizlet.
Hello everyone, welcome to Denver Startup Week. I'm Connor Swanson, the Developer Track co-chair along with Aaron Clark, and member of the Denver Startup Week Organizing Committee. Thank you for joining us for the 10th anniversary of Denver Startup Week. At Denver Startup Week, we strive to make all of our sessions a space where attendees can connect, learn, and grow, regardless of age, gender identity, gender expression, race, ability, or sexual orientation. A special thank you to all of our sponsors for their support in helping us to keep DSW free and accessible for all. Thank you for joining us, and have a great week.
Hello, everyone. My name is Dan, and I'm a backend developer here at Quizlet.
Hey there, I'm Josh Rye. I'm also a developer at Quizlet.
And we're here today to talk to you about the journey we've taken migrating from a monolith to microservices and moving a mountain of data along the way. The purpose of this talk is to share 3 major takeaways we've learned from 2 of our migrations, the answers service migration and the studiables service migration. We'll use both of these services as examples during this talk. So without further ado.
All right, I'm going to try to share my screen and play a presentation that we prepared for you. Is the Denver Startup Week host around to give me permission to share my screen, please? Okay, great. Thank you. Okay, can you all see this? All right, I'll take Dan's confirmation as everyone. Here we go, and let me know if you have any audio issues.
Here's the agenda for today's presentation. We'll start by introducing Quizlet and describe the problem we were trying to solve. Next, we'll identify the 3 inconvenient truths that cropped up repeatedly in our journey towards the solution. Then we'll walk through our migration, which we've broken up into 8 different steps here, but the process was largely similar between the two services. And lastly, we'll leave room for questions. So what is Quizlet? For anyone who is less familiar, Quizlet is the go-to study platform for learners globally to help them practice and master whatever they are learning. We provide students with digital study tools for homework guidance and test preparation to support their self-learning needs throughout the year. From flashcards and practice questions to interactive diagrams and games, Quizlet combines cognitive science and machine learning to intelligently guide students through adaptive study activities. In fact, we help over 60 million people each month, including 2 in 3 high school students and 1 in 2 college students in the United States. As one of the largest user-generated learning platforms, students and teachers can choose from over 500 million study sets on Quizlet or create their own, and learn or teach any topic imaginable. This includes traditional academics like languages, science, math, and history. People also use Quizlet to study for certifications ranging from nursing and finance to IT network certification, and for work and personal needs, like learning all the drink combinations at the coffee shop someone works at. To give you a sense of the scale of studying happening on Quizlet, over 1 billion questions are answered on Quizlet each week. And we're happy to report that 92% of students say they have better grades when they study with Quizlet. So what was the problem we were trying to solve? In recent years, we were hitting some scalability challenges, which we broadly put into 2 categories: scalability of data and scalability of development. Scalability of data means ensuring we can handle an increasing volume of data and traffic. We were feeling this challenge most acutely in 2 areas that we're discussing today. The first is what we call answers, which are users' responses to questions we present to them in different modes of study. Users' answers to questions, like the ones you see in the screenshot here, are used to track the user's progress learning that set. Today, we have well over 100 billion answers in our database, and we're often hitting that database over 4,000 times per second. Here, we see an example of the average latency of a select query to the answers MySQL table, gradually increasing over the course of 9 months, ending with large latency spikes as the table struggles to handle the load. The other area in which we were experiencing scaling issues was in a domain which we call studyable items. The studyable items, or studiables migration, stitched together 9 separate MySQL tables representing 1 unit of quote-unquote studyable information into 1 document. In the flashcard creation screenshot here, you can see a few examples of the tables that were migrated, such as the word and definition, the fake multiple choice options, and the image information. We currently have over 20 billion studyable items, not as much as answers, but these are much bigger and more complex data structures than answers, and most importantly, they power the core functionality of our business. What's Quizlet without its flashcards, after all? Similar to answers, you can see the average latency of our select queries to the table that stores our core flashcard data increase over the same 9-month period as the previous answers graph. Scalability of data isn't the only scaling challenge we wanted to address, however. Ensuring our developers can build new features quickly and happily as our code base, our product complexity, and our teams grow was becoming increasingly difficult with our unruly code base. As far as app code goes, the backend of our website and mobile API was a single monolithic app approaching 1 million lines of code, and it was littered with code related to answers and studyable items. And our ideas about answers and studyable items had evolved over the years, which led to some imperfect abstractions and awkward historical relics in our data models. If anything, we wanted to evolve even faster than before, but we were hamstrung by the weight of the code base. And even when we could wrangle the code, at our scale, we couldn't make some of the schema changes we want to without downtime, which wasn't an option we wanted to entertain. Here, we have a diagram showing our MySQL database model association mapping. The nitty-gritty details aren't important here for the purposes of our talk, but you can just imagine how adding a new node or modifying or deleting an existing node here might cause some unintended ripple effects. This talk is about the challenges we faced in addressing these scalability problems, which Josh will go over next.
The challenges to scaling that we face could be summarized as 3 inconvenient truths. The first one is that an organization's code, business, and team structure don't always evolve in stride. While you hope that these things do evolve in the same general direction over the long term, they might not be perfectly in sync every moment. This is really just a way of saying that you're going to have to deal with messy code from time to time in a fast growing organization. This can complicate the migration of code and data. This truth might be considered a wrinkle in Conway's law, which states that any organization that designs a system will produce a design whose structure is a copy of the organization's communication structure. The inconvenience involves the fact that an organization's systems and structure both change over time. For example, we've recently been expanding our product portfolio at Quizlet, and we reorganized our teams accordingly last year. That led us to draw a clearer team ownership boundary around studyable items. But at the time, studyable items accounted for a huge part of our product, and its functionality was widely dispersed across our monolith codebase, sometimes in ways that were a bit tangled with other teams' responsibilities. This lack of alignment added to the challenge of adding new features or migrating to a more scalable data store. Secondly, you need to understand your business and your problem well and think for yourself to solve it. This seems fairly self-evident, and maybe it's a stretch to call it an inconvenience, but we're offering this as a corrective to the desire and pressure that we sometimes feel to find a perfect out-of-the-box solution, or to find the answers to all our questions from a tech talk for that matter. It's helpful to learn about prior art, and nothing gets built from scratch, of course. But if you're expecting that some existing design pattern or technology can substitute for a close analysis of a complex problem, you're risking getting boxed into an inadequate solution. We'll see a couple of examples of design patterns that apply to our situation, but only up to a point. Finally, migration can be a project unto itself. The problem you're trying to solve might be hard even in a vacuum, but if it's in the context of existing software that's being used at high scale, and it's important to avoid downtime, then the migration becomes its own challenge, one that may even influence what your ultimate solution is. With that, let's take a look at the steps we took in migrating answers and studyable items to more scalable solutions. Here are the high-level steps. This is not perfectly sequential. And also, this is a distillation of a process we went through for 2 separate migrations for answers and then studyable items. So we're drawing from both of those efforts. But the story here is we built a microservice that does the work that we wanted to take out of the monolith and back to that service with a new, more scalable data store. In both cases, that happened to be Google's Cloud Spanner database. We refactored our monolithic app to introduce a clean interface in front of the behavior we're replacing that was relying on MySQL, and created an alternate implementation of that interface, which talks to the new service. We leveraged that refactoring first for write traffic, so that for all requests going forward, we would dual write data to both MySQL and the new service. We also had to backfill our new data store from MySQL for all the data up to the point where we had started dual writing. We had checks in place to make sure we were doing all this writing correctly, that what we were putting into the new database really was equivalent to what was in MySQL. We leveraged that monolith refactoring again, this time for read traffic, by gradually routing read-related method calls in the monolith away from the MySQL-based implementation and to our new implementation that read from the microservice. We then switched our dual write process so that the microservice became the primary write and our authoritative data store. And by then we were in decent shape, but there was still some significant follow-up work to remove final dependencies on MySQL and the old data models in our code. So let's run through this in a little more detail now, starting with building a new microservice. Building a microservice raised many questions, not least of which was, should we build a microservice? And for us, circa 2019, that question had two parts. Should we be building any microservices? And should we build one for the specific problem we were looking at, scaling answers at first and later scaling studyable items? These were among the many questions that we couldn't Google for a quick answer. We knew we were starting to outgrow our monolith, but moving to a microservices architecture is a big shift, so we had to ask if this was the right path for us. By the time we were getting truly concerned about our growing answers table, this question had been partly answered. We suspected that a judicious use of microservices would help Quizlet scale both our development and our data. This came from investigations and debate regarding our team velocity, our struggling deployment process, the need for different parts of our monolith to handle different rates of traffic and volume of data, technical limitations of our monolith's tech stack, and more. And we had already made some low-risk investments to explore the microservices path, building a couple of small-scale services to gain experience. Still, Answers would be our first large-scale mission-critical service, and we knew there would be some work needed to further build out our microservices infrastructure for deployment, visibility, monitoring, and so on. This contributed to our sense that this migration would be a sizable project. The next question was, should we build this microservice? Our investigations for answers and studyable items gave us confidence that there were data stores and tech stacks that could meet our data scalability needs. In particular, as I noted, we saw Google's Cloud Spanner database as a prime candidate. However, our monolith was written in Hacklang, a fork of PHP invented at Facebook, and this wasn't well suited to communicating via gRPC, which Spanner uses. This argued for building a microservice where we could choose a more suitable tech stack on top of Spanner. Whether building these services would help us scale our development was less clear-cut. We understood that to make a difference on that front, a microservice would need to cleanly encapsulate some part of our business and be owned by one team. And as Dan pointed out, answers and studyable items were not very well encapsulated in the monolith at this point, and were being touched by multiple teams. There was no magic wand that would immediately resolve that. Even so, we were cautiously optimistic that carving out a service would force us to better align our code with our product and team structure. But how much so depended on how much time we were willing to spend on that. But once we decided this was the right direction for us, more questions followed. One was the choice of tech stack. The critical decision on this front for both answers and studyable items was the choice of data store. And we landed on Google Cloud Spanner, a managed database on Google Cloud Platform, or GCP, because it has practically unlimited horizontal scalability, strong consistency, acceptable query performance for our needs. It's a relational database with full SQL support, and we were already a GCP shop. And just to flesh out this picture, here are some other key pieces of the stack that we settled on for both of these services. Designing the API and data model for the service is another key question. And in a way, this is where the rubber hits the road for our migration. Exactly which parts of the monolith are we carving out? This ties in tightly with the monolith refactoring questions, so we'll get back to this when we discuss that step. But we can mention a few things here. We decided to make these microservices internal to our network, so our monolith would continue to be our sole interface to the internet. And under the hood, it could delegate some or most of the responsibilities for a given request to the services. Along with simplifying some security questions, this decoupled our services APIs from our public-facing API, making it easier for us to iterate on them. We adopted a more or less RESTful approach to our API design, not always the most efficient option, but the easiest for our monolith to consume. And we made an impactful design choice for studyable items. They had evolved to be fairly complex and variable data structures. And we decided to encapsulate much of that complexity into a single JSON column in our spanner table. We deserialized it in the service code, but this greatly simplified the database schema and made it easier for us to iterate with new versions of this content. Load testing was another essential part of building the service to prove to ourselves early on that we really were on a path to address our data scalability needs. We used a tool called Locust, which was very helpful. But once again, we needed to think about what kind of testing was going to be meaningful for our particular situation. We gathered data about historical usage of relevant monolith endpoints to build a traffic profile that we fed into our load tests. For example, for studyable items, we looked at the historical distributions of the number of items returned for read requests, the sizes of those items, and a couple of factors influencing the complexity of the queries required. Just to give a flavor of the results we saw, we did some benchmarking of write traffic to an early implementation of our studyable items service using a mix of requests roughly mirroring our real traffic profile. And in a deployment of 20 service pods backed by a spanner instance scaled to 5 nodes, we achieved about 16,000 requests per second with median latency of 22 milliseconds going up to 130 milliseconds at the P99.99 percentile. Now let's take more of a look at refactoring the monolith. At a high level, we arrived at a refactoring approach similar to the branch by abstraction pattern, which works as follows. If you want to replace the original code in this picture, create an abstraction for it. Here it's called foo interface, implemented by old impl, which calls the original code. Create another implementation, delegator impl, which starts as just a pass-through to old impl. Change clients of the original code to call this new abstraction. Create a new implementation of the abstraction that calls out to our new microservice. Adjust the delegator so it can be controlled, possibly by some runtime options to decide which implementation it should use. Once you're confident in the new implementation, clean up the abstraction and remove the old implementation. So that all sounds nice, and it did pay off, but it belies the difficulties we faced in the refactoring, which partly stemmed from a kind of compounding of scalability challenges. Our answers and studyable item data models had evolved in such a way that in some ways they were inherently unscalable, regardless of whether they got stored in MySQL or anywhere else, because of the query patterns they required. For example, most studyable items consisted of plain text terms and definitions. We'd recently introduced the ability to format text with bold, italics, and so on. If a user chooses to do that, we stored both a plain text and formatted representation of it. You would think these two bits of data would in some sense be neighbors in our database. In fact, it required effectively 4 table joins to get them both. The irony is this inefficient and awkward arrangement was not just a cause of scaling challenges, but a product of them. There had been an effort to build a more flexible studyable item data model to enable formatted text and other features within MySQL, but under the constraint that the core legacy tables were essentially too big to alter. To ensure data scalability, we simply had to define a more rational data model for our microservice. But that made it harder to design an abstraction in the monolith that could accommodate both the old and new models. We ended up designing the monolith abstraction according to the service's improved data model, and then creating a shim layer, allowing us, for the most part, to translate between that and the MySQL-oriented data structures. So the introduction of the abstraction was much more intrusive than the branch by abstraction pattern might suggest. That cost was compounded by the fact that there were so many call sites in the monolith that interacted with the old style studyable items and answers models. But it kept us on the path toward data scalability. And this was an investment in scalable development as well. Introducing a cleaner data model helped that cause. And while the precise responsibilities we were carving out of the monolith and giving to the service were driven to some degree by pragmatism, having that clean separation at all was a win. The immediate fruit of this labor was that we now had a runtime lever to direct our delegator between the old implementation and the new service. This set the stage for our next step, dual writes. Starting with an empty spanner database, we weren't in a position to tell our delegator to start routing any read traffic to the service yet. We were now in a position to start writing data to the service. But how exactly would that work? The branch by abstraction pattern facilitates choosing between an old and a new implementation, but it doesn't really speak to methods that write data when the two implementations are writing to different data stores. And our plan to achieve data parity between the two data stores without downtime would rely on our being able to write data to both of them. Another pattern that gets closer to that problem is called parallel run. This involves calling both implementations, though usually with the aim of verifying that they're equivalent. Does this work for dual writing? To an extent, we're just talking about a simple enhancement to our delegating implementation. For any method that involves writes, have our delegator call both implementations instead of choosing one. For example, first write to MySQL, then to the service. But it wasn't quite that simple. For one thing, we had a trade-off to contend with on the question of whether to do the secondary write to the service synchronously or asynchronously after writing to MySQL. If we did it synchronously, we'd incur additional latency for the write calls, which might impact user experience. If we did it asynchronously, it would no longer be deterministic when the service's data store would be up to date with MySQL. We wanted to transition read traffic to the service while we were still in this mode, so we couldn't afford that much uncertainty. Just as a sidebar, why did we want to transition read traffic in this mode before we had switched to making the service implementation the primary write? Because making that switch was going to take still more work, as Dan's going to cover. And we wanted to prove out our read capabilities as early as possible. Luckily, the latency hit from a synchronous secondary write to the service, while not welcome, turned out to be acceptable for our use cases. In many cases, our web and mobile UIs issue write requests as a background task. And even when they didn't, the latency penalty wasn't a deal breaker. But with that hurdle cleared, we faced others. How should we handle a failed secondary write? We didn't want to bubble it up to the user to be a user-facing error because we were still treating the primary write as the canonical call, the only one that mattered to the immediate request that we were serving. But we couldn't ignore it. Any loss of data parity would jeopardize our ability later to start serving read traffic from the service. Our solution here was basically a belt and suspenders approach. If the synchronous secondary write failed, we would kick off an async job to synchronize the relevant records from MySQL to the service. And we built in visibility, monitoring, and runbooks to handle write failures across this flow. Even this wasn't the end of the dual write story. There were many complexities around writing data where it made a difference which implementation did the first write in order to maintain parity. As an example, we've been relying on MySQL's auto increment feature to generate IDs for new records. We pass MySQL a null ID to trigger the ID generation. If we naively pass the exact same null ID payload to the service that we pass to MySQL, the service would fill in a different ID from MySQL's using its own ID generation scheme. There would then be no good way to ensure data parity, and we'd lose the ability to dynamically route read traffic between the old and new implementations. So we ended up taking the result of the primary write, which included the MySQL generated ID, and passing that to the service, which would accept the ID it was provided when saving this new row. This decision will have an impact on a later step, so Dan will be coming back to this. The takeaway message here is, once again, a smooth and safe migration takes work. Was it worth the effort? Was this really better than just accepting some period of downtime while we switched everything over from MySQL to the service? We're convinced it was. That switch involved so much changed code, so many new moving parts, and such a large volume of data that we couldn't have given a time bound to that downtime with any real confidence. Having a robust dual write mechanism gave us so much freedom to migrate all the other code related to reads and shift read traffic with a strong safety net. Before we move on, a note about design patterns. We actually hadn't heard of the branch by abstraction or parallel run patterns when we were doing this work. We came across them after the fact. And they're helpful in communicating the gist of some of the things we did. Had we known them beforehand, it would have given us a more concise vocabulary for thinking about these problems. But we're not sure it would have caused us to work all that much faster or better. Design patterns can sometimes be a trap as a tempting substitute for thinking about your particular problem. So in a way, we were glad we didn't know those terms.
So even with a shiny new Spanner database, we still had years of historical data in MySQL. How did we get that old MySQL data into Spanner? Answer, we backfilled it. Our backfills needed to be repeatable and idempotent. It'd be too costly to first isolate the records that exist in MySQL, but not Spanner, and backfilling only those records. Instead, we wanted to be able to run a backfill on large batches of data without having to worry about which individual records were already in Spanner. We also needed to run the backfill multiple times, once before dual writes was enabled, and once again after dual writes was enabled to fill in the missing data. We ran the backfill once before dual writes because we didn't want to risk slowing down user-facing requests with a large bulk load job. For these reasons, the backfill needed to be repeatable and idempotent. We also needed the ability to run a targeted backfill for specified records so that we can efficiently patch up errors and other missing chunks of data. Like I already mentioned, we needed to run the backfill a second time after dual writes was enabled to fill in that missing data. And it's obviously much more efficient to target only those records in that time window rather than every record a second time. We used Google Cloud Dataflow since we were already using the GCP suite of services. Because Google Cloud Dataflow is distributed across multiple machines, we were able to run multiple jobs in parallel. The backfill for the studybles migration worked as follows. First, since we use BigQuery as a backup for our MySQL data, the first step was to query BigQuery for all of the data to be loaded into Spanner. This query will take data from all 9 MySQL tables and export that data into its own Spanner table, which we'll call BQ results table. One row in this file had all the data needed to create a single studyable item entry. Then we created an application in the studyable service called BQ to Spanner, which pulls data from that BQ results table and passes that data to a transformer sitting inside the service. The transformer will create a properly formatted studyable item entry in the main studyable items Spanner table. With this setup, we were able to backfill the studyables data in less than a week. When we were starting to write to Spanner, how could we tell that we were writing data correctly? One way to tell is by looking at the data parity between the two data stores. Are all of the records accounted for, and is all of their data consistent? Well, if we're using the output of writing to MySQL as the input for writing to Spanner, well then shouldn't the data just be automatically correct? Turns out, we expected data parity to drift over time for a few reasons. The first were because of secondary write failures. When dual writing, there were instances where the primary write to MySQL was successful, but the secondary write to Spanner failed because of issues such as network failures or Spanner or service downtime. This meant that a record or an update to a record exists in MySQL, but not in Spanner. Another reason for data parity decreasing over time is because we simply missed migrating a few MySQL call sites, but this was expected. To find out which call sites we needed to migrate for the studyables migration, we attempted to log the stack traces that led to any saves or updates to the 9 MySQL tables included in the migration. But we still expected to miss call sites like those coming from infrequently running cron jobs or other call sites with low call volume. For these reasons, we experienced growing data disparity. Another reason we wanted to verify the correctness of the data is because it enables the core functionality of our business. What's Quizlet without its flashcards? Because of this importance, we simply had to be sure our migration worked as intended. The comparison of two models presented its own challenges, however. One would think that a migration is working correctly only if every field for a record in database A matches every field for that same record in database B. But we learned that that's not actually the case. For example, during the studyables migration, we saw a large disparity for the last modified timestamp field of a record. This happened simply because a single studyable item entry only has one last modified timestamp field in the document stored in the service. Whereas on the MySQL side of things, that same record is represented by more than one table, each with a different last modified timestamp. Do we keep these MySQL timestamps in sync? If not, which one do we use as the source of truth for our service? Because the field was not critical to the functioning of the code, we decided that the work required to address this was not worth the effort, so we simply allowed the disparity. This is another example of how, at first glance, a problem encountered during a migration should have a straightforward answer, but that's rarely the case. So how did we mitigate the disparities? First, we increased the resiliency of the second write to Spanner. If the secondary write to Spanner failed, we kicked off an async task to retry the write to Spanner so as to not interrupt the user. Executing these retries asynchronously also allowed us to configure exponential backoff, which would give the overwhelmed service some time to return to a stable state. Then, we implemented an async task that compares the newly written data after the secondary write. The data parity checker takes the IDs of the models saved in the service, reads the models with those IDs from MySQL and Spanner, and compares their data. If a disparity is detected, we increment a disparity metric and log the disparity itself. We created a few graphs for visibility here. On top, you can see overall data parity percentage with an SLA of 99.9% correctness, which is represented by the green dotted line. On the bottom, we have a graph showing data disparity by field. That, coupled with logging, we were able to catch any missed or improperly migrated call sites quickly. In either case, when we noticed overall data parity slipping, we made corrections to the monolith code and ran a sync script to correct that data. But this sync script works a little differently from the backfill we mentioned earlier. The sync script works as follows. First, we generate a file using BigQuery again as the input to the script. Unlike the backfill process, however, this input file is only the studyable container /set IDs and not the studyable item data itself. When generating this file, we specify a date range to sync all of the records only in that range. In batches, the script pulls all of the studyable item data for that ID from MySQL. No transformer is necessary here because we use the MySQL persistence code from the monolith, so the return value from this get operation are already properly formatted studyable items ready to be sent to the service. We take that shimmed MySQL data and pass it to the service directly for saving, which syncs the data between the two data stores. Next, we'll discuss migrating read traffic. We obviously wanted to ramp read traffic gradually rather than bombard the service all at once. So we used percentage-based runtime options to slowly redirect traffic. For example, the studyables migration encompassed 9 MySQL tables, so we decided to have a runtime option per table. We have an internal UI that we use to quickly change the values of these options in production. Our main concern when ramping read traffic was in the sheer complexity of the monolith code. If all of the reads going to various MySQL tables are now hitting a singular service, are we making more HTTP requests than necessary? Additionally, we migrated over 40 call sites for the reads portion of the studyables migration, but due to the complexity of the code, we weren't confident that all call sites would hit the service properly. This speaks to how the migration itself is a first-class problem. We couldn't simply flip a switch and have the entire site read from the service and expect everything to work. Instead, it was more of an iterative process where we'd first ramp one table, observe the impact of the additional load on the service, look out for errors coming from the monolith, make any adjustments as needed, and continue on to the next table. The incremental migration of read traffic allowed us to gain confidence in performance, correctness, and stability of the service. Another inconvenient truth is that code and business needs don't always evolve in stride. We felt this during the studyables read migration ramp, where we had to halt the migration because of a redesign to our search feature. Our search feature allows students to search across set names, individual flashcards, textbooks, and schools. The redesign made use of the studyable service, but there was an unexpectedly problematic query that basically brought Spanner down. We tracked down this hard to detect query and met with Google engineers to rewrite it to be more Spanner friendly. But since the search redesign was deemed more important because it was user facing, we had to turn off the read migration while we figured out the best way to deal with the search redesign query. Making the service the canonical source of truth means making the service, or Spanner, the primary write and MySQL the secondary write. Should be as easy as switching a runtime option, right? Wrong. We had a few challenges to overcome before making the service canonical. And one challenge was that we rely on MySQL's auto-incrementing mechanism to assign IDs to new models. On this slide, you'll again see how the dual writes works. Like Josh explained in the dual write section, when saving a brand new model, MySQL assigned an ID to this model, which was also used in the service. We came up with our own ID generator for the service, but this way of handling IDs presented yet more questions when switching to canonical. How do we keep these IDs in sync since each data store assigns IDs in a unique way? Would this even be an issue? Is the canonical switch reversible? If we made the switch to using the service as primary and encountered a data disparity, would we revert back to using MySQL, or would it be easier to simply correct these disparities and move forward? Similar to migrating the read traffic, making the service canonical wasn't as easy as flipping a switch from the old system to the new system. In the case of our studyables migration, our old and new systems were coupled in a way and not fully independent from each other. We migrated several relational models over a new document model where these relationships are now implicit. So even some of the old data like IDs in the MySQL join tables is now irrelevant. If you recall the branch by abstraction pattern Josh mentioned earlier, making the service canonical isn't even a step of that migration strategy, which speaks to how the migration itself can be a first-class problem with many unknowns. We can't make Spanner our canonical data store before we have a backup and disaster recovery process in place, though. Although Google has introduced a backup capability for Spanner, the last time we checked, it was too slow for us to run it at the frequency we'd like for our databases of our size. So we implemented another data flow process to back up our data to the Google Cloud Storage, and we use Apache Airflow to run this job on a schedule.
At this point, we've removed just about all dependencies on our MySQL data, but there are still a few significant tasks that remain. We've lumped them into one final cleanup step in the interest of time and slide real estate. First, we still need to port the last remaining front-end dependencies on MySQL specific data. For studyable items in particular, some of our front-end code was so tightly coupled to our MySQL data models that it even needed things like the IDs of join tables we were using. Join tables that no longer exist in our document structured spanner data. There's no way to shim that, so we kept it around until this point, and now it's time to port them to talk in terms of the new style studyable item model. Additionally, some of our data pipelines use MySQL to populate our offline analytics databases, and those needed to be adjusted as well. And at that point, we can retire the MySQL tables. But even then, that isn't necessarily the end of the migration. The shim layer that we introduced in the monolith allowed us to keep some remaining code that works in terms of the old data models. Maintaining that is still a drag on our ability to fully leverage and iterate on our new data model. So we've got to port that code too. This is part of the cost of better aligning our code with the way our business and our teams are organized. And then we can rest. So to recap, the problems that led us to migrate all this code and data were problems of scalability of data and of development. We went on a long journey to not just build a more scalable microservice, but integrate it with our monolith, transfer a lot of data, and leave our monolith in a little better shape than we found it. And that process was made more interesting because of these 3 inconvenient truths. Thank you so much for your time, and we hope this was useful.
All right, that's what we've got. And we left some time for questions, so happy to entertain any questions. So I see a couple of questions from John Gunter. How did you convince your product team to take on the cost and time commitment of the migration? And how long did the entire migration take? I think, I mean, I guess I would say I feel fortunate that our product team does recognize the value of long-term investments. So it wasn't as much of an uphill battle as it might have been. Yeah, but I think it kind of speaks again to the sort of 2 aspects of scalability and then how they relate to product. So you know, we were feeling some pain in the data scalability department. For instance, you know, some of our answers queries were failing, and that was leading to a poor user experience. Even more commonly, it was causing really high latency, sometimes in a sort of a blocking way to the user experience, particularly for our most active users. For instance, because we hadn't really sort of optimized these use cases, there were some pages where you know, we were looking up tens of thousands of answers records in a single query just to compute some aggregate stats. And in fact, that is one optimization we did in answers service, which, you know, we had much more freedom to do kind of within the bounded context of a service to kind of implement aggregations and, you know, optimize those sorts of requests. So this was translating to poor user experience in some cases, and that certainly got product's attention. And, you know, even more kind of a long-term sense, we tried to make the case of like the improvements to the data model that we're making and sort of like sloughing off some of the historical baggage that we'd accumulated would just provide us better developer velocity. And so, kind of could go through a laundry list of features that should be much easier to implement once we were fully transitioned. And how long did the entire migration take? I'm terrible with timelines and memory on this front, but I believe the answer's migration was on the order of a year. If someone at Quizlet who has a better memory than me can refine that answer, please do chime in. Studyballs has been a beast, and we're actually still in the kind of final stage or later stages of the switch to canonical step. So that's not done, and we're well over a year into that already. So probably going to be, I would guess, approaching 2 years for that. Thank you, Amol. 9 months for the answers migration. Any other questions? I don't see any in the chat right now. Well, we could hang around for a minute just to see if anything comes up. All right, I think we can call it. Well, thanks so much for listening, and yeah, we hope this was helpful.
Yeah, thanks for joining, everyone.
And I'm not sure how to end the meeting, but signing off.